This video is our second video on intermolecular forces. The first video covered what the intermolecular forces themselves were. In this video, we're going to focus on the effects that these intermolecular forces have on boiling point and vapor pressure. If you've not watched the first video yet, please go watch that first, then come back. We'll begin with a quick overview of what we'll talk about today. We'll start with a discussion of what intermolecular forces are. This was already covered in video 1, but I want the ideas to be fresh in your mind while we discuss what we're talking about today. Then we'll dive right into our two topics. First, we'll talk about boiling point. We'll define what boiling point is. We'll talk about the general trend we expect to see in boiling point, and we'll then talk about the effects that intermolecular forces have on that trend. We'll repeat that process with vapor pressure. We'll define what it is, we'll talk about the general trend we expect to see, and then again we'll talk about the effects of those intermolecular forces. Over to the right, we see a picture of the ocean. I bring this up because it's very closely related to the concept of vapor pressure. Vapor pressure, as we'll know in a moment, is a measure of how much of the gas is released by a liquid under certain temperatures. We'll talk about the fact that as those temperatures increase, the pressure of that gas, or the amount of gas released, is going to get higher. As we experience the effects of global warming on our planet, that causes our oceans to release more water vapor into the air, increasing the concentration of H2O in our atmosphere, which is itself a greenhouse gas, further accelerating the process. This is known as a positive feedback loop, something you might have talked about back in your biology classes. So to begin, we'll start with a discussion of intermolecular forces to remind you of what these actually are. Intermolecular forces, if you recall, are attractive and repulsive forces between molecules and atoms of a sample. We're going to focus primarily on the attractive forces that we're going to be dealing with in this section. And those forces are primarily electromagnetic. They're caused by the dipoles that exist in the compounds, typically from some sort of polarity. We also discussed the fact that these intermolecular forces vary in strength due to a couple of different things. First of all, they can vary due to the type of intermolecular force you're dealing with, as well as the differences in the structures of polarities of these substances that affect the strength within a single force. Some dispersion forces are weaker, other dispersion forces are stronger, and in the previous video we outlined criteria that would cause those differences. Last but not least, here's a list of the forces we were talking about: dispersion forces, dipole forces, and hydrogen forces. And if you recall, hydrogen forces were the strongest of the three. And generally speaking, when we're talking about trends today, it's these hydrogen bonding forces that are going to cause the most disruption to the properties of boiling point and vapor pressure. Let's start with the definition of what boiling point actually is. It's a measurement of when the average molecule has enough kinetic energy to escape the intermolecular forces holding the particles together in a liquid. These particles need to gain enough speed to allow them to overcome the forces holding them together. And if you recall from previous discussions, those forces holding them together are going to be our intermolecular forces. We'll continue then with an explanation of our general trend. In most cases, we can expect that the boiling point of a substance will be most closely related to that substance's molar mass. Down below, we have the equation we've talked about. Down below is an equation you should hopefully be familiar with from your previous year in physics. It talks about how kinetic energy is equal to 1/2 times the mass of a particle times its velocity squared. Earlier in this unit, related the idea of kinetic energy to the concept of temperature. Temperature is a measurement of average kinetic energy. Looking on this side of the equation, we can consider the velocity of our particle right here, and we can decide, or we can discuss the fact that there is some sort of minimum velocity needed for a particle to escape the intermolecular forces holding the liquid together. And if we reach that minimum velocity, that particle will be able to leave the liquid phase and enter the gas phase. Taking that into consideration, we can then see that if we increase the mass of our sample, which in this case will be related to the molar mass, we would expect that the kinetic energy would have to go as well, assuming that this constant velocity we needed to escape is some constant value. So heavier particles require more kinetic energy. Taking that one step further, since kinetic energy is proportional to temperature, that means that the temperature at which this is going to happen, the particle escaping the liquid, is going to be higher. And if you think about it, that particle escaping the liquid has to be what our boiling point is all about. So in short, we can say that as mass increases, we expect the boiling point of our substance to increase. Taking a look at this plot, we can see that happening here with actual data. In this plot, we have molecular weight, or the mass of the compound, plotted on the x-axis. We have temperature plotted over on the y-axis. And what we can see as we look at these different substances and all these different compounds is that in general, as their molar mass increases, as we go from left to right on the chart, there is a general upward slope in the temperature at which these materials boil at. So we can see that in general, the boiling point of a substance increases with molar mass. Now you might have noticed that there are 3 compounds over here on the left side of the graph that don't seem to follow those patterns. These compounds, despite having extremely low molar masses, tend to have very, very high boiling points compared to their counterparts. That is because these substances have something special going on. These 3 compounds, water, hydrofluoric acid, and ammonia, are compounds that meet the criteria for having hydrogen bonding. And the presence of those hydrogen bonds, those very strong intermolecular forces, disrupt the pattern that we normally see in molar mass. Let's see if we can't put some of this information into writing. First, we can say that boiling point increases slowly with molar mass, which we explained on the previous slide with the kinetic energy equation, and we're showing here with the dark blue line. We can also say is that boiling point increases dramatically with the presence of more intermolecular forces, especially with the presence of hydrogen bonding. So we should be able to predict the boiling points relative to one another of substances using information about molar mass, as well as information about the types of intermolecular forces present. Let's see if we can't put some of those ideas to the test by placing the 4 compounds below in order of increasing boiling point. Lowest boiling point listed first, highest boiling point listed last. Based on our discussion previously, we talked about the fact that the first piece of information you're going to need to determine this order is the molar mass data of these 4 compounds. Some quick calculations tell me that CH4 has a molar mass of 16 grams per mole. CH4O2 has a molar mass of 48 grams per mole. C5H12 has a mass of 72 grams per mole. And C2H6O has a mass of 46 grams per mole. In a lot of cases, you don't actually have to do these calculations. You can actually estimate. We don't need to know what the molar masses are. We just need to know which ones are bigger, which ones are smaller. In this scenario, some of the numbers were a little closer, so the math made a little bit more sense. Now, in the previous graph, we saw that molar mass was only half of the battle. The other thing we need to be aware of is what intermolecular forces are present in each of these substances. Well, if you look at your information from the last video about identifying intermolecular forces, the first thing we can say is that all of these compounds are going to experience dispersion forces, as all compounds do. Because all of them experience dispersion forces, it's probably not necessary to list these out simply because it's going to happen every single time, and we're more interested in differences in electromagnetic force or intermolecular forces. Looking again, the next force we'll be interested in is, do they contain dipole forces? If you recall, dipole forces require the molecules to be polar, and the only 2 polar molecules in these substances would be CH4O, so this is dipole, and C2H6O, this guy will also contain dipole forces. Last but not least, we have to detect whether or not there's hydrogen bonding present. That requires a hydrogen directly bonded to an oxygen atom, a fluorine atom, or a nitrogen atom. You would have to draw a Lewis dot structure to know this for sure, but both of these guys are going to experience hydrogen bonding. So again, looking at the three structures, we can start thinking about how to put them in order of increasing boiling point. The lowest boiling point compounds are going to be the ones that contain no intermolecular forces. We talked about the fact that the molar mass trend is a much weaker trend than the intermolecular force trend, so anything without those intermolecular forces is automatically going to be the lowest. In that scenario, it's solely the molar mass that's going to determine their order. This would tell us that CH4 is going to have our lowest boiling point, and C5H12 is going to have our next highest boiling point. Now this leaves these two compounds here. When you draw the Lewis dot structures for each of these, you're going to find that CH4O2 actually has more opportunities for hydrogen bonding than C2H6O. This guy has one hydrogen-oxygen bond, so you can think of that as being hydrogen bonding times 1, whereas this compound has two hydrogen-oxygen bonds, meaning this has two places for hydrogen bonding connections to form. This means CH4O2 has more intermolecular forces than C2H6O, and we can place them in order accordingly. After C5H12, we'll say C2H6O is going to be our next substance in terms of increasing boiling point, and last but not least, the CH4O2 will have the highest of the 4 boiling points. There are some worksheets available on the download section of my webpage, as well as other places on the internet, that can allow you to continue practicing this, and we'll practice more of these in class. Let's move on to our second property we'll be discussing, vapor pressure, something you're probably a little less familiar with. The definition of vapor pressure is located over here on the left. It's the pressure of gas that is exerted as that gas collects over top of a liquid during evaporation. You can imagine, because of evaporation, all liquids always have a small amount of gas of that liquid floating over the surface. We can see this happening in the picture over here. You can imagine that as all these particles in the liquid are colliding with one another, there is going to come a time when enough of those particles all collide with the same other particle at the same time, transferring enough momentum and velocity so that this particle will have enough to escape the surface of the liquid and become a gas. Certain liquids do this more, meaning there is more gas present and a higher vapor pressure. Other liquids do this less, and that would mean that there is less gas present and a lower vapor pressure. When we talk about things that have a higher vapor pressure, what we're really talking about is that these substances are likely going to be described as more volatile or more likely to enter the gas phase. This implies that there are fewer forces holding the liquid molecules together, and it also probably implies that this substance also has a lower boiling point. I bring that up because what you're going to find as we discuss this is that the explanations for why vapor pressure is affected by intermolecular forces is very similar to the way we describe how boiling point is affected by intermolecular forces. Just like before, to establish our trends, we're going to take a look at a graph. This is a graph of vapor pressure on the y-axis, measured in the unit of torr, something we're not super familiar with. We'll be talking about a little later on the unit. It's simply a unit of pressure. And temperature on the x-axis. Looking at this graph, we have plotted information for 3 separate compounds. We have diethyl ether, ethanol, and water. And just like before, we're hopefully going to see that difference in these compounds translate into expected differences that we can see in the actual value for vapor pressure as well, connected to intermolecular forces. The first thing we can interpret from this graph is that vapor pressure increases exponentially with temperature. The warmer your substance gets, the faster the evaporation process is going to be, and the larger the cloud of gas over the source of your liquid is going to get. Next, we can identify in the graph that when the vapor pressure is equal to the atmospheric pressure around it, that means you must be at the boiling point. Looking at the graph, this is actually marked. 760 torr, or 760 millimeters of mercury, is normal atmospheric pressure. This graph has a horizontal dotted line drawn that intersects the 3 of these, and it creates 3 points. This point for diethyl ether is 34.5 degrees Celsius. We get a point for ethanol at 78.5 and a point at water for 100. You're probably not familiar with the boiling points of diethyl ether and ethanol, but you are likely familiar with the boiling point of water as 100 degrees. This idea of atmospheric pressure makes a lot of sense. You can imagine the atmosphere pushing down on a liquid, holding the particles in the liquid phase, and then the liquid's pushing back up. when the liquid can push the particles back up as hard as the atmosphere pushes down, we would expect to see more and more particles being released into the atmosphere. That would be our boiling process. So our first two bullet points identify the general properties or the general trends we would expect to see on this graph. The next thing I'd like to talk about is what effect intermolecular forces have on the vapor pressures of these three substances. Generally speaking, we can expect that vapor pressure will decrease when there are more intermolecular forces present. This means that the particles are less likely to enter the gas phase with more forces holding them together. There's going to have to be a much higher velocity for those particles to escape the liquid if there are more forces holding those particles in. We can actually see this depicted on the graph when we take a look at this particular temperature, 20 degrees Celsius, which is relatively close to room temperature. This vertical dotted line shows that the vapor pressure of diethyl ether is the highest of the three, where the vapor pressures of ethanol and water are significantly lower and similar to one another. To understand why those vapor pressures spread out like that, we need to know a little bit more about diethyl ether, ethanol, and water. So shown at the top of the page here are the Lewis dot structures for the three compounds, diethyl ether, ethanol, and water, along with their relative molar masses. Just like before, if we want to understand why these three chemicals have the vapor pressures that they have, we need the molar mass data along with the intermolecular forces data. Looking at these three compounds, we would expect all three of them to have dispersion forces. I'm not going to list those out because that's not going to help us decide. The two most polar compounds in the group are definitely going to be ethanol and water, meaning these two contain dipole forces. We might suspect that diethyl ether would also contain very mild dipole forces, but I would expect that those would be low enough that we could actually leave them out. Last but not least, when we consider hydrogen bonding, all three compounds contain hydrogen atoms and oxygen atoms, but in diethyl ether, the oxygen is not attached to one of the hydrogens. Therefore, we had no hydrogen bonding here, but we would expect to get hydrogen bonding with ethanol, and we would expect to get hydrogen bonding with water. Now, just like last time, in ethanol, there is one place for hydrogen bonding, so we get that hydrogen bonding times 1. However, water has 2 hydrogen bonds in it, so we're going to get more of an effect for water. Comparing this back to our chart over here in the bottom, we can again start to see why these three substances have the three vapor pressures that they have. Diethyl ether had the fewest intermolecular forces present, and as a result of that, there was very little holding the compound in the actual liquid state. This means diethyl ether would release a lot of chemicals into the air, which explains why diethyl ether's vapor pressure was significantly higher than that of ethanol or water. Ethanol and water, on the other hand, have similar intermolecular forces, dipole forces, and hydrogen bonding, and as a result, they have similar vapor pressures. Water's vapor pressure is slightly lower than ethanol's vapor pressure, mostly due to the fact that there's a higher degree of hydrogen bonding in water than we see with hydrogen bonding in ethanol. Overall, what I hope you see from this problem, as well as the problem we did with boiling point, is the general philosophy for solving this is the same. Identify molar masses, identify intermolecular forces that are present, and use the differences in both of those characteristics to sort these compounds in order of increasing or decreasing property. And that brings us to the end of our video today. At this point in time, you should be able to define what boiling point and vapor pressure are. You should be able to explain the effect that intermolecular forces have on both of them in general, as well as specifically for each intertype of intermolecular force. And finally, you should be able to interpret the plots of boiling point and vapor pressure like we saw today as a tool for identifying what those general trends are, as well as being able to explain why there are exceptions due to the presence or absence of intermolecular forces.